Welcome to Lecture 2.4, Solving Linear Equations. So first let's handle some terminology here. What is a linear equation? Well, in one variable, it's any equation that can be put into the form of ax plus b equals 0, where a and b are real numbers and a is not 0. Well, a could be 0, but then it's not very exciting. It's just b equals 0, and therefore b equals 0, and that's not very exciting. So we do make the statement that a cannot be 0, then it's a linear equation. So we have some solving strategies for solving linear equations in one variable. Step 1 is to use the distributive property to separate all our terms. If there are fractions, you can decide to either eliminate the fractions by multiplying each term by the LCD at that point. The next is to combine similar terms. Now step 2 is you use the addition property of equality to get the variables on one side of the equation and the constants on the other side of the equation. I like to generally have my variables on the left-hand side and the constants on the right-hand side, but that's up to you what you prefer, as long as the variables are on one side and the constants are on the other side. Step 3 is we use our multiplication property of equality to get the variable isolated. And then step 4 is to verify true solution. For example, we want to solve 2x plus 3 equals 10. Our first rule, let's distribute the 2 across the x plus 3. 2 times x is 2x, 2 times 3 is 6, and 10. So 2x plus 6 equals 10. Let's use our addition property of equality to get our variables on one side of the equation and our constants on the other. So 2x plus 6 minus 6 equals 10 minus 6, leaving us with 2x equals 4. Now, using our multiplication property of equality, I can either multiply by 1/2 or divide by 2. So 2x over 2 equals 4x over 2, leaving us with x equals 2. But again, that's not enough. You do need to verify that 2 is a solution to the original problem. So here's the question. Is 2 a solution of this problem? If I insert 2 for x, then I am left with 2 times the quantity 2 plus 3. Does it equal 10? 2 plus 3 is 5, so 2 times 5, does that equal 10? 10 equals 10, yes, it does verify. That is the solution set for this problem. Let's check another problem. 3 times quantity x minus 5 plus 4 equals 13. So the first step is I can move the 4 over. Okay, so let's get the 4, the constant of 4, over to the right-hand side of the equation. I'm going to subtract 4 from both sides, leaving us with 3 times quantity x minus 5 equals 9. Distribute the 3x minus 3 times 5 equals 9. Do the multiplication of the 3 times 5, so I'm left with 3x minus 15 equals 9. Move the 15 over to the right-hand side by using our addition property of equality, adding 15 to both sides. That leaves us with 3x equals 24. Divide by 3 using our multiplication property of equality, leaving us with x equals 8. But again, we need to verify that that is our solution. So we're going to plug it back into our equation. Wherever we see x, we're going to place an 8. X minus 5 equals 3. 3 times 3 is 9, plus 4 is 13. Yes, 13 does equal 13. I know if you did your problem in all the steps correctly and you've gotten a solution, that should be good enough, right? But it's not. You still have to verify, because what if? What if you accidentally subtracted something incorrectly up in your process? By verifying your solution would not check out. and therefore you would figure out that, oh wait, I need to do the problem over again because I actually did do something wrong in my process. For the smaller problems, you may always feel like you got the right answer, but still verify. Just like with fractions, we have two methods when dealing with decimals. The first method is we just work with the decimals. The second method is we eliminate the decimals. Okay, so let's work through the first method. I want to solve 0.08x plus 0.09 times quantity x plus 2000 equals 690. Okay, I'm going to use my distributive rule to distribute the 0.09. So I have 0.08x plus 0.09x plus 0.09 times 2000 equals 690. The 0.09 times 2000 is 180. So now I have 0.08x plus 0.09x plus 180 equals 690. I'm going to combine like terms for the 0.08x and the 0.09x, giving me 17x. Oops. I'm going to subtract the 180 to bring my constants to the right hand side, leaving me 510. I divide by the coefficient, which is 0.17. If I divide both sides by 0.17, x equals 3000. Sometimes working with decimals isn't very fun, so we have another method. We can eliminate the decimals by multiplying. In this case, I need to get the decimal amount over 100. So if I multiply everything by 100, I should eliminate the decimals. So let's restate our problem. Now I'm going to multiply the left-hand side by 100 as well as the right-hand side by 100. The whole entire side. 100 times the whole entire left-hand side equals the right-hand side times 100. By multiplying 100 by 0.08, I get 8x. 100 times 0.09 is 9. I want to say that is one term. Therefore, I'm going to multiply the 100 by the one term, which is 0.09. And now I get 9 times the quantity x plus 2000. And then the right-hand side is just 69,000. I add like terms. I move the 18, or I distribute the 9 across the x and the 2000, leaving me with 8x plus 9x plus 18,000 equals 69,000. Subtract the 18,000 from both sides, leaving me, and combine like terms, 17x equals 51,000. Divide by the coefficient of 17, and my result is still 3,000. So whether you want to work with decimals or not is up to you, but remember this one step. The 0.9 times a quantity is one term. You're only going to do the multiplication once. You might want to expand everything first and then multiply each term by whatever value you want, but that would have given us a little bit more work. What I mean by that is if my problem is 0.08x plus 0.09x plus 180 equals 690. Then I have to multiply each one of the terms by 100, not just the center group. So if I multiply everything by 100, I get 8x plus 9x plus 18000 plus equals 69000. Whether you can understand that it's, or that you prefer, I should say, keeping the term together, or first expanding the term using the distributive rule, that's up to you. You'll still get the same amount in the end. All right, let's work on this problem. 7 minus 3 times the quantity 2y plus 1 equals 16. First, I'm going to distribute the negative 3. 7, 3 times 2y, negative 3 times 1 equals 16. Okay. 7, and do the multiplication. 6y minus 3 equals 16. Next step I like to do is to combine like terms if I can. So 7 and negative 3 is negative 6y plus 4 equals 16. Now I'm going to get my constants on the right-hand side and leave my variables on the left-hand side. I'm going to isolate my variable by dividing by the coefficient. So y equals 2. All right, we'll say, here's why you check your solution. So I'm going to plug 2 back into the original equation. And work this problem. 4 plus 1 minus 7 equals 16. 4 plus 1 is 5. 7 minus 3, 5 equals 16. 7 minus 15 equals 16. Minus 8 does not equal 16. Here's the reason why. I accidentally dropped a negative. Right when I divided, I only divided by 6. I did not divide by negative 6. So if I bring it back to negative 6y over negative 6, 12 divided by negative 6, my true solution is negative 2. But again, I'm going to go and check to see if indeed negative 2 is the correct answer, the correct solution. 2 times negative 2 plus 1, does it equal 16? 2 times negative 2 is negative 4 plus 1, negative 3, 7. And negative 4 plus 1 is negative 3. Negative 3, 7. 7 plus 9. And 16 does equal 16. So I know my solution is indeed negative 2. So until next time, be seeing you.